we understood about the concreteness being added to refinement number 1 and 1. And let's see how we can accordingly mathematically declare the state space and also the invariant conditions. Let's see how we can do that. And we start with the static part. The static part is simply being shared among M0, the abstract model, and M1, the refinements. So we have the same set of carrier sets, constants, and axioms. Let's just recall them very quickly. We have the two carrier set. We got the set of data items, just carrier set. We don't have to specify exactly what the membership is for D. That's the abstraction we are applying. And also the Boolean data type, either true or false. That's one of the axiom over here, as you can see. And also the constant N and also F. Let's recall what they are specifically. N will be the size of the sender file. So you can think about the sender file can be formulated as more like an array. So remember in lecture 1, when we did a math review, you can check that one of the exercises is about how to formalize an array. So it's going to be a function between the set of index values to the data elements. So in this case, we assume that the indices will be from 1 to n. It's more like an interval. We'll see that in a moment. We also need that for declaring the invariance. And F will be the sender file. You can see axiom number 2. F is a member of the set of total functions between 1 to n. So that'll be the indices for the array. So you think about, in this case, the indices will be starting from 1 rather than 0. But it may start with 0, but we just choose to start with 1. Doesn't really matter as long as we're consistent. Well, there'll be a total function from 1 to n to each domain value between from this interval set over here 1 to n is going to map to some value from D. And also we assume that the array is non-empty because n is larger than 0. Right? That's something you want to recall from the earlier part when we talk about the initial model. And the dynamic part for the refinement is going to formulate a gradual transmission process. Specifically, we're going to see how the sender file is going to be transmitted to the receiver side piece by piece or element by element, indicated by the index R, as we saw in the earlier part for the abstraction. We'll take a look. And so these are the three variables we're going to use. So it will be the Boolean variable B and also the H, which will be what has been received so far on the receiver side. And also it will be some private index on the sender side, which we can also use to really specify exactly what has been received so far on the receiver side. And for simplicity, we are not actually going to have a typing constraint for B being a Boolean anymore. That's something we did earlier in the initial model already. We can assume that B is a Boolean type. But you can see invariant 1,1 over here specifies the typing constraint for the R. You can see R is ranging from 1 to n plus 1. So that means it can actually go up to and including n plus 1. So you can think about n plus 1 is exactly one of the maximum index for the sender file array. That's something you can keep in mind. But we'll visualize that as well. And you can see as the usual pattern, we better do some exercises together about specifying the invariant conditions rather than throwing the answers to you and take them for granted. That's not the way to go, right? We're gonna do 3 conditions together. 2 of them will be invariants, and the other one will be theorem. And I'm gonna explain about the difference between the invariants and also theorem over here. There is some important detail you have to pay attention to so that when you generate a sequence for refinements, you wouldn't get confused. That's something we'll talk about. Okay, let's now move on to the page over here. So we got our static part over here as we just went through, and also the dynamic part. We got the 3 variables, and we got these 3 conditions to be specified as exercise. We'll go over them one by one. Let me first of all clarify about between invariance versus theorem over here. For invariants, as we said before, they ought to be proved for establishment and also preservation by the various events. They need to be proved. To be proved for establishment and preservation. Right? That's about invariance. What about theorem, THM? The theorem actually has a slightly different role over here. The theorem over here, number 1, need not be proved for establishment and preservation. Establishment and preservation. That's the first fundamental difference you have to know between invariance and also theorem and preservation. And number two, well, if it doesn't have to be proved for establishment in preservation, so do we need to prove the theorem anyway? The answer is yes, you have to prove it. So the way you prove it is about, given the invariance you have over here, can you derive them into the theorem? That's something you want to prove. To be proved as derivable from the invariance. That is, given all the invariant conditions as the hypotheses, can we actually prove each of the theorems as a go? And of course, here we only got one single theorem, so that's why there's only one single theorem to be proved. But if you got multiple theorems, you have to prove their derivation from the invariant conditions one by one. So I do have some exercise for you a little bit later, but let's now focus more on just specifying the conditions over here, and then we talk about the proof later. Just understand that the way you prove about invariance would be different from the way you prove about theorem. You just want to understand that first. Okay, let's now do the exercise together. Invariant number 2 would be 1, 2. Elements up to index r-1 have been transmitted. This one seems a little bit odd over here because it may be a little all of a sudden I'm talking about this particular condition, but it's not actually quite natural based on the concreteness that we spoke about earlier. Let me try to give you a little bit of intermediate context over here, so it'd be much easier for you to do this exercise over here. All right, let's talk about it. You can think about this is the initial configuration over here. For the initial configuration, I want you to pay attention to where R is. You can see R is actually over here. After transmitting the first item, R will be pointing to the second item. After transmitting the second item, R will be pointing to the third item. After transmitting the third item, R will be pointing to one of the valid indices of the sender file, right? You can remember so now you can see why R should be in the interval of 1 up to n+1. So this is exactly n+1, which I spoke about earlier as well. Let's see how the R over here can really help us derive what has been received on the receiver side. So that's a formal relation we like to draw, and we want to specify that as an invariant condition, which can be proved for establishment and also preservation. So what pattern can we really observe from the receiver process? Let's take a look. And I'm just going to make this example more precise. Let's fill in more details. What about f over here? F is basically a total function. And let's enumerate exactly the members in the total function. Remember, a function is basically a relation. A relation is simply just a set of pairs. So in this case, what would be the pairs for f? It would be exactly the indices 1, 2, and 3. 1 maps to A, 2 maps to B, 3 maps to C. So that's exactly the typing constraint we saw over here, right? That's about f. And you should really make sure you understand about this part over here. F is actually a total function over here. And let's write it down. So f is going to be 1 maps to A, and also 2 maps to B, and also 3 maps to C. That's what we have. And you can see here, 1 here, 2 here, and 3 here. So these are the domain values, and you can see we cover all the domain values. So indeed, it is a total function. And it will be the largest index. In this case, it will be 3. All right. And let's now try to see exactly how the value of R is changing as the transmission process is ongoing. Initially, R is just the value of 1. Okay, let me use the pink value over here. And it will be incremented to 2, incremented to 3, and also incremented to 4. What does it really mean when R value is actually equal to 1? That means the first item is ready for transmission, but not yet. And for R being 2, that means item at index 2 is ready for transmission. And more importantly, all the smaller indices in the standard file have assumed to be transmitted successfully. Okay, it's really important to see that. Think about it this way. Since the index is over here, that means whatever that's before the index have been transmitted over here. So this part here is really corresponding to this part. And then after that, when the index value is actually 3, that means all the smaller indices, the corresponding elements have been transmitted successfully to the receiver side. In this case, because r is equal to 3, that means indices 1 and 2. The corresponding element have been transmitted to the receiver side. Right? Hopefully the highlights can actually help you over here. And finally, when r becomes 4, in that case, that would mean from index 1 to index 3, all the corresponding elements have been transmitted successfully. Okay, let's now also highlight it over here. This one here, and also this one over here. And what kind of pattern can we really observe? Let's see this. The pattern really is the r value. There are two purposes. Number one, indicates the r value indicates two things. Which element is to be transmitted, but not yet. And number two, what elements have been transmitted. And for this one here, it's going to be from index 1 all the way to index r minus 1. So this is really where the r minus 1 came from in the hints. Let's see how we can visualize it. In the case of this, you can see here, we got element at index 2 being ready for transmission. So that would mean the elements at index from 1 until 2 minus 1, which is over here. This will be the range. They have been transmitted already. Let's take a look at another example. When r is actually equal to 3, what does that indicate? It indicates, number one, element at index 3 is ready to be transmitted, but not yet. So that's point number 1. And point number 2, all the elements at index from 1 until 3 minus 1, which will be 2. So index 1, index 2, they have been transmitted to the receiver side. Right? So these are the two important insights you actually want to remember. Okay, so which element is to be transmitted, and more importantly, what elements have been transmitted already. So that's the r minus 1 you want to really pay attention to. Right? How does that help? Let's take a look. You can see here, when r is equal to 1, in that case, h is really just an empty set. And when r is equal to 2, that one there, h is basically is index 1, right? We always start the indices with 1. It's basically just 1a. And when r is equal to 3, in that case, we are index 1, index 2, and we got 1a, and we got 2b. And finally, when r is equal to 4, we got index 1, 2, and 3. And the corresponding h will be 1a, and also 2b, and also 3c. These are the corresponding value for h. When r is equal to 1, this is the value for h. When r is equal to 2, this is the value for h. When r is equal to 3, this is the value for h, and etc. Now, can you actually answer invariant 1, 2? This is really to try to draw a formal relation between the h over here and the value of r. And you may also want to refer to f as well. Right? I think enough hints about, I'm not really directing to you exactly to the answer, but I think there's enough context for you to think about. What we want, before you pause the video, what we want is a Boolean condition over here. That one there is going to draw a formal relation between the value of r, f, and H. We want to say elements up to index r minus 1, as I explained earlier, have been transmitted or to the receiver side. Right? You can now pause the video and think about what a Boolean condition should be for the invariance. Alrighty, assuming that you thought about it, I think for the empty set, it's always some boundary case you want to consider. Let's consider that a little bit later. What about this one here? You can see apparently this is a subset of the F. Agree? And also this one over here is also a subset of the F over here, only up to here. And similarly, this one over here, the final receiver's file, the complete copy of F, is an entire set of F. It's always a subset. And what's really more precise is about this. I want you to look at the domain value over here. You can see this one here is 1. This one here is 1 and 2. This one over here is 1, 2, and 3. Can you see any connection between 1 and the 2 over here, and also 1, 2, and the 3 over here, and also 1, 2, 3, and the 4 over here? That's really the kind of pattern we would like to formalize and generalize from the example. That would be your invariant condition, right? Let's now take a look. It would be something like this. Let me suggest something here. Okay, so this one, let me say star. So the star should be, the H is going to be, what kind of relational operation can we use? Well, in this case, I would suggest we use domain restriction. And it should be restricted to exactly from 1, but not really until R, because R is only the elements, is only indicating the element to be transmitted, but not yet. So only from 1 up to R minus 1. So this is an interval set, right? It's an interval. And I can just make some annotation for you. You can think about this is really a set, which will go from 1 and then 2 all the way to R minus 1. Right? That's more like conceptually it is the case, but you should really understand about this notation here. And I want to use that as for restricting the domain. So I would say this one here, domain restriction, and then we can say F, and that's it. And of course, I'm assuming that you understand about how the domain restriction works. If you don't, you definitely have to review the lecture number 1 about the math review. And think about this. When R is actually equal to 1, in that case, 1 minus 1 is going to be 0. What will be the interval set from 1 to 0? From 1 to 0, that one is a very special one. If you actually want to talk about, let's say, interval from 1 to 0, in that case, the upper bound is actually strictly less than the lower bound. In that case, it would just be equivalent to just empty set. It's a special case you want to remember. Okay, that's something I can actually talk about right away. Right, so this actually formula will work when R is equal to 1, because in that case, you're trying to domain restrict to some empty set over here, right? This will be just equal to the 1 up to 0 domain restricted to by F, right? So this will be just equivalent to empty set. This will be how we apply the formula for the first one. What about the second one? The second one here is also is going to work, because here we got R being 2. So 1 up to 2 minus 1, and then being the restriction for the domain of F. And if you try to double check, it's also going to match the value, right? Because this one here is only going to be a singleton set of 1. That means we're only extracting 1A to be here from F. Right? For completeness, let's now finish the other two. This one will be equal to, the R value is actually equal to 3. So R minus 1. So 1 up to R minus 1, which will be 2. That will be for the restriction of the domain of F. Right? So that's the next one. And the final one over here, this one here is equal to, the R value is actually equal to 4. So 1 until 4 being used as a restriction for the domain for F. And you can see this one over here is exactly the domain of F. F domain restricted to the domain of F is going to get the original f. It's a simple property, you can definitely argue. In that case, this will be the complete copy of the original f after the transformation is completed. Right? So this formula is going to work, right? This will be our first invariant. That might be the trickier one to actually to come up with. That's why I spent so much time to help you derive it. What about invariant 1,3 over here? Let's look at the hints. Transmission completed will actually mean no more elements to be transmitted, right? How do we actually indicate that? Let me give you some hints. Whether or not transmission is completed is indicated by the Boolean value b, and whether or not there is more element to be transmitted somehow depends on the value of r, because you can see if r is really a valid index still for f. For example, r is 1 is equal to 2 equal to 3. That means we got more element to be transmitted. However, when r is just 1 off the maximum valid index of f, in that case, that means we have no more element to be transmitted. That'll be the hints for you. Right? You can now pause the video and figure out what invariant 1,3 should be. Alrighty, assuming that you thought about it, let's now take a look. Right? Invariant 1,3 over here. Let me just say star star. Okay, star star over here. So transmission completed, that will suggest b is exactly equal to true. Right? That one's easy. That means a conditional invariance implies no more elements to be transmitted. This is really the case where we got no more element to be transmitted because r is exactly 1 off the maximum index of f, right? So this means no more transmission, right? So what does that mean? That means r is equal to n or other value. If r is equal to n, that means we still got the last element to be transmitted. So r is equal to n is not the answer. That should be n plus 1, exactly 1 off. Because n plus 1 is not a valid index, meaning that we have no more element to be transmitted. Right? Plus 1. Right? So far we got 2 answers. Right? This will be the first one over here. This will be invariant 1,2. And also we got the second one over here, invariant 1,3, which is over here. And let's now talk about the final one. And this one here is just a theorem. As I said before, that should be handled for its proof separately. But let's just focus on what it should be as a Boolean condition, like a predicates. The theorem should be, we want to say transmission completed means, so this part here should be similar to this, I can tell you. Receiver has a copy of the sender's file. What does it really mean when the receiver got exactly the same copy of the sender's file? Meaning that contents-wise, they are the same. So this is really the case, right? You can see this is the final case where once we do the domain restriction, what we got is exactly equal to f. Right? That's a hint for you. Right? You can now pause the video and think about what this one should be. Alright, assuming that you thought about it, let's now take a look. And for that one there, let me use green. Okay, let's say we want to figure out theorem 1. Let's now say star, star, and star. So star, star, and star. What should that be? Well, it's going to be conditional, right? So transmission completed. That means b equals true. Implies receiver has a copy of sender's file. That means the receiver's copy, which is h, is exactly equal to f, right? That one's rather easy. You can say h is just equal to f. So that'll be the theorem that we want to prove somehow. But the proving process will be separate from invariant establishment and also invariant preservation proof. Let me recap what we have done so far. We have figured out the 2 invariants over here and also the 1 theorem over here. You should really understand about the derivation process. I think that's more important. Okay. And then let me just go back to the slide. There's one more thing I would like to mention, and before we actually move on to proving the invariance. Right, so these are just something we have gone over. And how do we prove a theorem or a property that's derivable from invariance? What you want to do is, as I said before, you want to take all the invariant conditions as the hypotheses because they should be derivable to each of the theorem that you declare. That's something you want to prove. So what you will do is you're going to do this, right? So you want to put all the 3 invariant conditions as we derived, and then as the hypothesis for a sequence, and the theorem will be the goal. That will be something you have to prove. All right. So hopefully the thinking process now is clear to you. And for this one here is rather straightforward. Usually when you declare something as a theorem under the invariant section, you're rather confident that given the invariance over here, each of the theorem will just be a byproducts for the invariance. So given that, we're going to prove that all the invariant conditions over here, 1, 2, and 3, are going to be established and also preserved. The byproducts logically will be this theorem will also be implicitly established and also preserved. We don't need to explicitly prove any proof obligation related to the theorem preservation and establishment. We don't have to. There's only one single proof we have to conduct about the theorem, which is given these hypotheses, this will be entailed. That's what we're going to do. And that will be the exercise I want you to do over here. Okay. And before we move on, so that's the exercise you want to complete first about how to prove this sequence here, so that we can always use this theorem if we need to later.